Alright, so we are live. And again, nice to see everybody. Glad to hear some of you folks had a good weekend. Hopefully the rest of you had a good weekend, or again, we're exactly halfway through the semester. I think this is week 7 of 14 or so. But with that said, just a little fun warm-up to get us going here. How many folks, maybe let me start with this question. I'll dim the lights so you can see a little bit better here. Let's see, that's a little bit better. And let's go about maybe halfway up. Let's go all off here so you can read. How many folks have ever heard of this website or YouTube channel called Handmade Hero? Has anybody heard of that here? No? All right. Well, maybe you will someday. But so it's just for fun thing to get you familiar with this. There's a really cool YouTuber or developer. He's worked professionally for many years. His name's Casey Muratori. And a few years ago, he created this thing called Handmade Hero, where he just builds everything from scratch. Meaning no libraries for building games, no SFML, just to really show how everything works from the ground up. Maybe some of you have that. I know this is something I certainly always want to know, like, how does this stuff work? How does even SFML work? How does this algorithm work? So anyways, really cool, or in my opinion, YouTube channel and website here called Handmade Hero. And anyways, he started running this conference called Handmade, which just showed how to build all of these different software projects, again, from scratch. So no abstractions, no, magic or mystery, right? So you get to see exactly how stuff works. Fast forward a few years, and now they run these sort of handmade conferences for programming. And there's one coming up called Handmade Seattle, where they give really cool talks, and they tend to be sort of systems focused. So the stuff that we're talking about, for instance, when we're talking about the heap and the stack and how stuff works in C++, the folks that love that stuff are, giving talks and presenting a range of materials at these sort of things. So from beginner to expert level, you can find all sorts of talks, and they're all available free online as well, as many things are these days. So anyways, just want to kind of bring that to your attention. If things are gripping you or getting you interested, or especially if you're interested in systems programming, this might be a conference to take a look at. Just see, how the, how it's made from scratch. Okay, so, and I'll actually be gone November 16th, so I'll remind you, because I'm going to go give a talk here on memory allocation and some of these different things. So there'll be a recorded lecture for that. But something to think about. And again, if this isn't your cup of tea, as the expression goes, maybe you'll find conferences in your area of expertise or your field that you really enjoy later on. So you can go give talks, network with folks, and talk about the stuff that you like to talk about. So just something to keep in mind, and of course I'll remind you or post that talk if it gets posted soon after. All right, so just something fun to look out for. And let's go ahead to the course logistics, and then we'll talk about what we did last time. Let's take a peek at the website here. So here we are, again, as I mentioned, halfway through the semester, according to my calculations. Let's see, 27 modules, so we're at 14, exactly half. And last Wednesday, or might have been on Thursday at some point, Assignment 7 on image processing, sorry, ignore this binary tree part, was released. So hopefully folks are working on that. If for some reason you don't have Assignment 7 in your repository, please let me know. Should be a fun one. Another one where you're going to be practicing with manipulating 2D arrays. But the sort of progression with Assignment 7, so you'll be implementing some different filters to build a sort of, you can think of it like an Instagram or a Photoshop type of operations that you'll be doing, right? Making grayscale images or filters. But in a sense, you're sort of on your own, meaning that I'm not going to supply you with any support code in it. So, you get to decide, what's the abstraction going to be? Are you going to have classes for your pixels? maybe you'll have a bunch of functions. So I think there shouldn't be too much of a leap as far as understanding how to work with 2D arrays, but the leap is going to be, now you have to write the program from scratch, because I think we're ready for that. And this tends to be a fun assignment. So you have a little bit of freedom. Make sure you're getting started on that. Any questions about assignment 7, what's going on, or just other course things from folks? Yes, yeah.
I guess I looked at it a little bit already. Is there a specific kernel you want us using for the edge detection?
For the edge one, I think you can find some folks have posted on Piazza about it. There's a ridge detection filter that'll do a decent enough job. Some folks found this Pruitt kernel, which is fine. That's actually 2 kernels that you sort of get to work together. That's fine too. And you'll likely find a bunch of other different variations of kernels on the web. So they'll give, so the results might be slightly different, but you can kind of look at the example image I provided. If it looks like something like that, right, where you're detecting edges, that's fine. Okay. Yeah. Other questions from folks? And of course, if you find other cool filters or kernels that you want to apply, feel free to add more. That's part of the going further section. Always welcomed. All right. Anything else logistics-wise? If not, feel free to grab me after class. We should have some time today. With that said, let's go ahead and dive into Object-Oriented Programming 3. So I have our slides here, activity, bunch of videos here. You don't have to watch all of them, but if there's a particular topic that grabs your attention or you didn't understand, there will be videos always. So for today. Before we get into today, let's talk about what we were doing last Wednesday. Spent some time talking about shallow versus deep copy. So again, this was revisiting copy constructor and understanding why on earth would we have to build these copy constructors. Well, we found that the answer was, we're always giving a copy constructor and copy assignment operator from the compiler, which is nice of it. But unfortunately, the code that the computer writes for us, meaning our compiler, generally isn't that smart, meaning it was just doing a very naive assignment. So as we know, when we assign pointers to something, that just points them. If we have 2 objects that are creating copies, they'll point to the same location in the heap. And then it's very unclear who owns this memory, meaning when one of these objects goes out of scope or we call delete on it, which one is supposed to actually delete the memory. Okay, so that was the issue that we are sort of wrestling with or implementing. And the way to solve this is to implement your own copy constructor and do what's called a deep copy and allocate new memory for your object for this block of memory. So each object has its own internal storage. Okay. So that was what we worked on, and then you folks worked on this for your in-class activity. You implemented a fixed string, and I think hopefully that was interesting or fun to do. So I'll try to do some more in-class coding, things like that. And I think this is always a great way to learn as well. All right, so with that said, any questions about the deep copy and shallow copy stuff we were working on last time? No. So at that point, we have most of our special member functions, constructor, destructor, the copy constructor, the 3 musketeers, and then our 4th musketeer is the copy assignment operator. We have those covered, so we're doing pretty good as far as our C++ goes. That said, there is more. There's always more, and sort of in this domain of object-oriented programming. So round 3 of object-oriented programming, a few things that capture, again, the essence of what object-oriented programming is. Again, for those of you folks who have taken object-oriented design, 3500, CS 3500, you've seen some of these things, but we need to see them in the C++ context so that we can keep expanding what we can do in the language. Okay, and 2 of the important things that are part of object-oriented programming, composition and inheritance. And in fact, we've used some of these perhaps without giving a name, although, again, if you've done this in Java, you know the names, right, either from Fundies2 or OOD, of some of these tools, composition and inheritance. But let's look at it from a C++ standpoint. So again, we've talked about how to create our custom data structures using things like struct and class. Those are our two tools, again, very similar. And what we're doing when we're creating some new data type usually is building it out of other building blocks, other data types. So over on this example here, I've got here, it's just called pod for plain old data type, right? And this just has 3 floating point values. So the way we're aggregating x, y, and z to make some other type, and then this other flag for important or some integer here indicating that. Okay, so that's one of the things that we've seen how we can do. But we might want to add some more power to this particular data structure. And we've also seen that one of these other key attributes of our object-oriented programming is this idea of encapsulation, this idea that we can put together some data, maybe it's x, y, and z, with some actual member functions, some actions that would work on this data. Right? So we could write some functions here to return x, or maybe compute the length or something of this value, or even we know that there's constructors, destructors, all related to this particular object, and for each instance of that object that'll act on its own data. Okay, that's the stuff that we've talked about previously, this idea of encapsulating all the functionality of the code and the data together. Okay, and then we've got some other little things that we've learned about as well. Being able to mark some of this data as public or private, again, to sort of create, what's legal or what can we do with this object. So actually, if you run this code, we're going to get an error because this is private, this important part here. So this will flag, the compiler will give us an error there. All right, so those are just some of the object-oriented programming things we've looked at. But part of this, even with creating these 3-member variables, x, y, and z, we're composing together those data types to build some other bigger data type. So we call this composition. Okay, and when we compose something of something else, we say that that particular data type has that component inside of it. So we say it has a relationship. How many folks have heard has a before? Again, most OOD folks, hopefully, yeah, instructor used that phrase. If you haven't, let me reveal it. So about 50% of the class or so is taking OOD willingly. So composition, what is it? A reminder to some, a new idea for others here. This idea that we're, again, composing different data types together to make something new. Now let's just draw your attention here to this example. Let me use my laser pointer to point to it. But I've got 3 data types here: a structure for wheel, another structure for engine, and a class here called car. Okay, so this is sort of the classic or the canonical example of how to build different components, right? Your car, if you're a driver or have ridden in a car, everybody, right, should have some number of wheels and an engine, right? So I'm able to build up this actual object, or sort of lay out this object in memory, this car, with some number of wheels and an engine. Okay, so we say car has a wheel, and car has a engine. Or in this case, since wheels are even within vector, we'd say car has a vector of wheels, just to be very specific here. Okay, so we can have any number of wheels on our car: 2, 3, 4, 5, 6, etc. Okay, so that's the idea. That's what composition is. That's composing, making up this object of other ones here. Okay. All right. So this is one way in which we can create new types in C++. Again, this is what we've been doing previously. Okay. So this particular type of composition. I guess we'd say there's a couple types. But this is, again, aggregating some other types here that sort of live inside of car here. Okay, so every car has, this vector of wheels, and every car has an engine here. Okay, so that's what it is made up of. Now, one of the advantages of composition is it's relatively easy to just see what's going on. Again, I don't think I need to overcomplicate things. Here, we can clearly see a car, what components it's made up of. There's no real mystery here. But we are sort of encapsulating, whatever an engine's supposed to do, whatever its functionality, right? It's over in the engine struct of the class, and that'll take care of any member functions or member variables or whatever are all isolated into engine. And likewise for our wheels as well. Okay, so it's relatively easy to see what's going on here. All right, so that's one benefit of composition. It's pretty easy to work with, pretty easy to understand. Depending on what types of applications you're building, it can be good for performance. We'll have to talk about that a little bit. But again, I think if I gave this to everyone and said, what are the components of a car, right, you could very easily see this here. Okay. Now this is in, so just showing the example below versus, if I was trying to model this car with either just primitive types or, something a little bit more rigid. This is still an example of composition, I suppose, right? We have a interarray here of 4 wheels with, 4 diameters and liters and cylinders. Basically, I've just gotten rid of our wheel and engine structures and just embedded everything into a car. So, sure, if you want to argue this is composition of instance stuff, but again, we can see that I haven't. This is the benefit we get by abstracting things into different components, right? Their own structures, and then composing objects of other objects, and not just primitive types or arrays here. Okay, so can everyone see that we probably like this example below here? Probably a better abstraction below here. So I think that's hopefully more clear. But we've got other things too with our primitive types, right? Line 15 and 16, you can see specifically, I have a bias, and I've said cars always have 4 wheels, or at least 4 in this case. Right? What if they have 6, or a truck or something that has 8 wheels? We'd have to get into messing around with dynamically resizing our arrays and these types of things, right? Just create a vector of the thing here and kind of compose and build up the types, right? This makes it a little easier for us to program. So again, we like to compose things of, these building blocks here. Easier to reason about. Okay, so that's one of the benefits of composition here. All right, now with that said, so that's composition. The one I want to, any questions about what composition is? And sort of aggregating things to build up a new type. All right, we can see that sort of clearly in here. How many folks in their fire assignment or an image processing are modeling pixels as red, green, and blue components? So some folks are. Yeah, you could treat it just as integers or individual ones, but again, think about how you want to break things apart into smaller pieces, and have a vector of pixels or something that have RGB components. Right, so definitely use these tools that you have. All right, so again, composition, one way that we can build up new object types from others. The other way that we can build new data types is through inheritance. Okay, and this forms a relationship. And this is what I want to talk a little bit more about. So we have composition and inheritance, and we'll talk. We're visiting these at sort of a high level today, but we'll see them a couple more times throughout the semester, or have to talk about them. But let's introduce inheritance here. And the way to understand this, I guess, it's like sort of classic family tree example, where, right, there's some relation between folks, right? So you'd say Mike is a Shaw. You ever hear that expression? Say, oh, he's a Shaw. My dad and mom and grandpa, etc. Right? We're all in the same sort of the family tree, so we have some sort of related traits, if you want to think about it genetically, or whatever traits you want to extrapolate from. That's sort of the same relationship that we're going to form in our code, right? Some sort of parent and child, or grandparent and parent relationship. Right? These are sort of related things. Okay, so that's the sort of conceptual analogy that we can give here. Well, let's look at it in code. I think it's a little bit more concrete and easier to talk about. So inheritance. Okay, so what is this tool here? Well, again, what we're talking about with object-oriented programming is, how are we going to create new types? Okay, proposition is our first tool. So what does inheritance mean? Well, let's just draw your attention to the top right here. I've got a little diagram here with fruit at the top and apple and banana below it, and then arrows pointing towards the fruits. So apples, an apple is a fruit, and a banana is a fruit as well. Okay, so that's the relationship that we're forming here when we talk about these objects, and we'll put it in code in a moment. Okay, so apple and banana are a fruit. Okay, they're related. They have seeds, whatever the qualities are that make a fruit a fruit. These things fall under some hierarchy here. Okay. All right. So another example here below, and this is one we'll work with a little bit in code for shapes. Same thing. We might want to put similar related things into some sort of hierarchy, right? They have some sort of relation to the other objects. So shapes, anything that sort of falls into this category, we have triangles. And then, we have different types of triangles, or right triangles, for instance. Other types of shapes, quadrilateral, which we could also say rectangle, with something with four sides. A rectangle is sort of a specific configuration of something with four sides. And then squares are also rectangles, right? Fall into this category. Okay, so you can guys see this hierarchy of related things. And again, shapes, all these shapes probably have some similar properties that we care about. So the ones we'll look at today, like if I wanted to compute the area of a square, that's something we can do, right? Multiply the length of the sides. Same with rectangle, the base times the height, quadrilateral, etc., etc., etc. Right? So this is the idea. We have a bunch of related things, and it's important for us in some way in our code to capture that these things are related. Okay. So, how do we talk about these things? I'll focus on the shape example because that's what we're going to look at in code. Again, the sort of relationships that these have. So the shape, the thing at the top, is what we call the base class. Okay, it's the base or the foundation, if you want to think about it that way. Okay, from which all other objects will be derived from. Okay, so this is our base class. Then we say triangle is derived from shape. It's gathering all the properties, deriving all the qualities of the shape here. Now, it might have its own unique properties as well, but at a minimum, it's all the things that a shape is. Okay, does that make sense for folks? Hierarchy. And you can see where the arrows are pointing when we're looking at this sort of inheritance diagram, right? Everything's going up to the shape. Okay. Depending on where you learn inheritance from or object-oriented programming, you'll also hear different names for these things. So I tend to use, this is the base class. Triangle is a derived class. Triangle is derived from shape. Again, different ways to talk about it. Sometimes folks will say shape is the parent, right? And triangle is a child class. It's a child of shape. That's acceptable. And most other times you'll hear triangle is a subclass of shape, okay, which is the parent or the base class. So you'll hear these different terminologies, so they are listed in words here if you want to see, but I like base and derived class. That sort of captures what's going on. All right, so with that said, let's go ahead and move to a little code example here. I've introduced one other thing here, which I'll talk about. And this is, if you're following along on the code, inheritance.cpp in our module. Inheritance. Here it is. And let's move this over here, and I'll get ready to compile it with debugging symbols, of course. All right, let's take a look at this here. Kind of give you the landscape here. Okay, so starting from line 15 to 26, let me just highlight part of this so you can kind of follow along here. So this is where I'm looking. Here is our shape class. Again, this is the top of our hierarchy, so I've got to define it first. Other things need to know about it. And what are the properties or the attributes, right, the member variables of a shape? Well, we have the area at line 17. Okay, so those are all things that shapes would have, right? We should be able to compute the 2D surface area here. Okay, and then the member functions we've got here, a function here called void compute area, and then another function here that returns an integer, a member function called get area. Okay, and that'll return the area. Okay, so that's our sort of base functionality that we would want any shape to have. Okay, including just a shape itself. Okay. And for today's examples, and if you play around with the code a little bit, you'll notice that another great way, as always, to learn these things is just to print out with a cout statement where or which actual function is being called. So here it's highlighted. I just have shape : compute area. Okay, because this is the compute area function that's found within the scope of shape. Okay, is everybody okay with that so far? I just got this shape where we're storing the area and a few member functions. All right, well, let's get into the inheritance part here. So I'm looking in around here. And let me move this a little bit higher for you folks. There we are. All right. So, we make a decision in our code to say, okay, we want to have multiple types of shapes that do something interesting. So we're going to create a triangle and derive it from shape, because we want this code to have all the properties of something that's a shape. Okay, maybe at least at a high level when we're thinking about using inheritance, we're saying, okay, at the very least, I want to reuse maybe some of this code. Okay, which is one reason to use inheritance, right? We get code reuse. But the stronger reason why we should use inheritance is because we're saying, hey, a triangle really is a shape. Okay, so there's some meaningful relationship. Okay, so how do I establish this relationship? Well, at line 28, I say class here, triangle, so create a new type just like I normally would, and then the colon and public shape here. Okay, I'll have to talk a little bit about this, but basically this says, hey, inherit everything that's publicly available from shape. Okay, that'll sort of be our default way of inheriting things. Okay. Now I could use something like private here, and then that'll inherit all the things that are, well, it won't really give us anything if I put private here, I guess. It's sort of, it'll give us all the private members of shape, and so. So does this much make sense of what I'm doing here to create the inheritance? Say triangle is a shape here. Okay, so now I get all the attributes here, including, well, what I had here. I had this thing here, area, so that's part of triangle as well. It's not listed under the class here, But because I'm inheriting from shape, I get all these things here. I get mArea here. I get this function here, compute area, and I get this get area function as well. Okay. All right. All right. And then for our triangle, right, it's its own thing here, right, with its own base and height, these member variables here. Well, I'll have my own constructor here. Okay. So we learned about constructors, of course. So here's one that takes in 2 parameters. And then I'm using this member initializer list here to establish that, yes, the base of this triangle is going to be whatever parameter I pass in. And the height of this triangle is going to be whatever height I pass in. Okay? And, well, here I guess I'm assuming it's a right triangle here. Oops. But base times height times 1/2. All right, so that'll be the area here. Maybe you should rename this. All right, and then our get area function here calls get area, and we return the area. Okay. All right, folks, okay with that? All right, so we'll have our own constructors for our classes, just like before. Okay. All right, and then I'm going to go ahead and repeat this. I've got my rectangle here, and well, a rectangle is a shape. So again, I'm going to inherit from shape, and public just means give me everything that's available, anything that's not, and then, well, a rectangle has width and height, okay, and then I do the same thing with the constructor. This time I'm not using the initializer list, but still computing the area here, and then I've got a get area function. All right. Okay, so let's go ahead and run this and see what it does here. And what I'm actually doing in the code is just creating a shape, computing its area, getting the area, creating a triangle, computing its area, and so on, and the same thing with the rectangle. Okay, let's go ahead and see what gets printed out. And I run this. And let's see here, what do we get here? So for our shape, we are calling compute area. We are getting the area here as well. And then for our triangle, well, I'm calling compute area. But where is it coming from here? Let's see. It's coming from shape compute area. Okay, so let me actually look back in our class here, in our hierarchy. Right, so within triangle, I've got just the get area function, okay, which looks like it's calling here. And then within our shape, I've got compute area. But again, compute area is not found in triangle anywhere. Okay, but let me split this so you can see both ends of the code here. So go down to our bottom here, right? So just in triangle, right, I'm able to call this compute area function, even though it's not defined anywhere in triangle. Okay. So let me highlight here these 2 functions here, right here. Okay. So does this make sense to folks? Triangle here, which is derived from a shape. I get or inherit all the functionality of things that shape can do. So even though within my triangle class here, I don't find it in this body code because it's inherited from shape, I get all of that functionality. Okay. Make sense to folks? Any questions? Okay, and again, because we're printing things out here, and again, let me make things maybe a little bit more clear in the output. Sorry, let's put some end lines here, just so we can kind of, again, give ourselves a little bit of a neater output here. Let's rebuild this, rerun it, right, just so we can see each time. Each time, right, when we're doing stuff with our triangle, between 66 and line 69, and then a rectangle, 71 and 73, we can see the associated which member functions are actually being called here, right? Some of them belong to the shape, some of them the actual class that we instantiated here, okay? We said, hey, this is a triangle and called compute area. And our compiler, again, is looking at this and saying, hey, you don't have the compute area function defined in triangle, right? We just have get area here. So it looks up the hierarchy to see if it finds anything called compute area. Okay? And that's what it proceeds to do. All right. Any questions about this? Inheritance round 1? All right. Cool. We're all on the same page here. This is great. Now the one thing also that we haven't seen yet is this guy here. This third access specifier, or at least I haven't talked about it. Maybe you've seen it, again, in Java. Line 16, protected. Does anybody know what protected does? We've seen public. We sort of know what that does. Makes everything available. We've seen private, which makes things only available to within the class, but we can't do .private something. What's protected do? Yeah.
Objects which extend shape have access to any area.
Yeah. Yep, perfect. So yeah, objects that are extending or derived from shape, extended is another good word, have access to M area, okay, within their class, so they can directly access this. Okay. All right. All right. Okay, so with that said, I want to go ahead and open up another example here in a moment. Some things that we have to start paying attention to when we're using inheritance is if I have a type that's derived from another type, how is that actual object getting constructed? So this is where, again, we have to think about, our constructors, and that they're always there, right? Even if we don't define them, right? There needs to be some way to build an object, right? So the compiler will give us one. But if I have a derived type, so if we think about our inheritance diagram, like right triangle, which was derived from maybe triangle and then shape, we have to call all of those associated constructors. And when the object goes out of scope, we also have to call all the associated destructors. Okay. Now I'll actually show you in what order. I think it's easiest to show in an example. So I'll open up another example from today called constructors, if you want to follow along. And it's following the same pattern, right? We've got a shape, just like we just saw. We've got a triangle derived from shape. And then we're actually going to increase our hierarchy one level further. We have right triangle, which is derived from triangle. Okay, so 3 levels here. Okay, so let's see what happens when we create a right triangle here. And this example is constructors. And so compiles. And before I run it, so here's all the code is doing here. Right, I'm just constructing one right triangle. I want you to just think about for a moment, what order would it make sense if I need to construct right triangle, which is derived from a triangle, which is derived from a shape. What order do those constructors need to be called in? I'll just let you think about it for a few seconds, and then we'll go ahead and run it. Okay. And as well, think about the order that needs to be constructed and then the order that needs to be destructed. All right. Everybody have their answers in their head. Think about the construction and destruction order. Again, this was the important thing we learned about last week. RAII, resource acquisition is initialization. It's important that we have this sort of deterministic construction and destruction for things like inheritance. So let me go ahead and run it. Hit enter. And let's see what happens. To construct a right triangle, well, the first thing that we have to do is our foundation. We have to build the shape. And then shape, well, we're constructing then a triangle and then we construct the right triangle finally. Okay? So right triangle, that's lowest on our hierarchy, right? Shapes at the top. Just draw here so we have it. Shape at the top. Above it. Below triangle is derived. And right triangle. Okay, so shape has to be built first, our foundation, and then the next layer, triangle, and then the right triangle. Okay. Now the order that we have to destroy things then, well, it sort of happens in the opposite order. So the first thing that's going to be destroyed is our right triangle. That's at the bottom here, and we can see the little destructor here. And then we can destroy the triangle that was allocated, and then finally the shape here. Okay? So it forms sort of a stack here. We construct the shape, put that in, then we construct the triangle, put that on top. If you want to think about this as building up an object, we put in the shape and construct it, and then the triangle, T for triangle, and then R for the right triangle. Okay, that's the order that we create things, and then we destroy them by picking whatever is on top of the stack. The right triangle, the triangle, and then the shape. Okay. Does that make sense on the order of construction and destruction? Now, why is this going to matter? Well, this example that we have here, relatively trivial here. But it matters if, for instance, let's complicate things a little bit just to make it a little interesting. If I create some data here that's going to be dynamically allocated, and maybe I decide here, right, for this data, for whatever reason, this would be kind of a weird design, but I decide that I'm going to actually allocate it inside of the triangle. Right, data equals new int 10 or something, and then maybe I'm going to delete it in right triangle. This is getting a little bit wild, right? I'm sort of allocating memory in a different place and deleting it, but this should still work as long as we're not, deleting twice in our hierarchy. We only need to delete the actual data one time. So this will actually work. But if I do this, right, I put delete the data twice, right, this destructor is going to get called, and this destructor is also going to get called. Okay. So again, we want to avoid those double frees and just pay attention to where we're allocating our resources. Okay. Again, usually in the class where we create things. Okay. Does that make sense to folks? Yeah. All right. All right. Well, let's see. All right. So that should give us a pretty good foundation of, creating some new types, again, where we want some relationship to be established between them because they are, in fact, related, right? And they're supposed to have some relationship. Okay, so let's keep advancing things a little bit further here. So what I want to talk about next is this idea of polymorphism. And in C++, we're going to refer to these one type of polymorphism as virtual member functions. Okay. Now, previously we've seen a type of polymorphism. I think maybe in the first week or two I might have mentioned this. That we can have functions named the same thing. I can have two different add functions, and depending on their arguments, right? This one's adding integers. Second add functions adding floats and returning a float. The compiler can figure out which function to actually call. In fact, it figures it out at compile time. It says, okay, you put in two floats here, or return a float. Okay, you meant this one, right? They're named the same thing, so the compiler doesn't need to just use the name to resolve, which actual function to call here. Okay, so that's one type of polymorphism, which is really this idea of having many forms, right? This add function has many forms, two in this case, right? Adding integers and returning an integer, and adding floats and returning a float. One type of polymorphism. And again, we could figure this out at, when our program's compiling, which one to actually use. Okay, so that's the idea here. So in C++, when we start working with inheritance and we're trying to figure out, hey, we've got this hierarchy of shapes and rectangles and triangles. What happens if we want a particular shape to behave differently? For example, let's say I have some function here, like for our area, where I say, well, by default, all of my shapes are going to have a width and a height. Okay, so there's some constraint here, I suppose. Here, and to compute the area, that's just the width times the height here. Okay. Okay, so that's fine here. But let's say I derive something else, a rectangle, okay, which would have maybe a different area function, or I suppose a square or something. I guess they're all going to resolve to be the same in this case, but the point is I want to override some behavior of something in my hierarchy. Okay. Now, the first thing I need to figure out is this allowed? Can I override this default behavior here from area? In order to do that, my way to signal this is to put virtual in front of a member function. Okay, so we only use this for member functions, not regular functions. With virtual here. And what virtual means is, hey, when the program's actually running, so the program's, we have to have compiled it successfully, and then when we type in /prog to run the program, then we'll figure out or resolve which of these area functions we're going to call. And the one that we're going to call depends on the actual type of the object. Is it a rectangle or is it a shape? Okay. Does that make sense for our folks? Okay. Now, a rectangle is a type of shape, but we do still have a type here for a rectangle. Okay. So let's look at this example here, and I'll run it in a moment here, where I've got a pointer to a shape here, S1, and I say equals new rectangle. Okay, so this is actually something a little bit new here, because previously we've only seen what's at line 44, right? This should look relatively normal. At line 44, where I say a pointer to a shape, S2 equals new shape, right? We create or allocate enough memory for a shape. But I can also do this here. Why? Because a rectangle is a shape. Okay, so I can have pointers from a base class to the derived type. Okay. Does this make sense for folks? As long as these are in the same hierarchy, we can create types in this manner. All right, and then we have an area function in both of them. Now, again, the question is, which version of area is called? Well, let's go ahead and see what happens here. Okay, so let's go ahead into our virtual example. Here it is. Okay, and let's see what happens here. All right. Okay, so again, shape here, creating a rectangle, and that'll be the first instance where we call area, and then a shape, we just say, hey, that's a new shape. Okay, so if I run this, well, at line 42, the first one that's printed out, it's calling the rectangles version. And again, that should make sense, right? We're actually creating or allocating the memory for a rectangle here. Okay, so we should be doing the things that are a rectangle. Okay, and then likewise over here, S2 equals new shape. We call area here. Okay, does that make sense for folks? Question? Yeah.
So in like the previous example, I know you didn't like define like an area function in like the triangle or whatever it was class.
Yep.
That wasn't didn't say override, it didn't say version, but it still worked, right?
Yeah, still worked. And because there was only one version of the getArea function in our base class. So let's actually see. I mean, that's an interesting. Should we just see if we don't mark this as virtual, what happens? Let's get rid of it. Let's recreate what we had before. Let's just have area here first, and let's just comment this out here. Okay. So we just have area in our base class, and let's see what happens. Okay, so it compiles, it runs. So no decision to be made at this point, right? Rectangle, we say, hey, we don't have area, but we are a type of shape. We look up in our hierarchy and we find a function here. Okay. So let's get rid of this. And this is exactly, this is the next activity, actually, for me to do. Let's go ahead and, okay, let me get rid of all this stuff here. Now, and let me make sure you can see everything. Rectangle has area and shape has area here, but no virtual, okay? So my question is for folks to think about, at line 41 here, right, I'm saying here's a pointer S1. I'm saying create a new rectangle. Again, that's legal, right? Because this is a type of shape. And then I call area from S1. What's it going to print out here? And then here, line, this is 44, I create a new shape and then call area. What's it going to print out? So let me let you think about that. And again, we don't have any virtual, so there's no runtime decision here that's going to say, hey, when this program actually runs, figure out, are we a rectangle or are we a shape? Okay, what's the actual memory allocated? Yeah.
In line 41, why would you want your pointer to be a shape pointer instead of a rectangle?
I'll show you why in a second. Yeah. And actually, we'll do all permutations so we can see. Okay? We'll put rectangle on the other side and see what happens. Yeah. All right. So everybody's thinking about what is this actually going to print out now? No virtual, so I can't see anything. All right. So let's go ahead and let's save this. Let me bump it up a little bit higher so you can see. Okay. Yeah, last seconds to think about this. Let's recompile. And now I'm going to rerun. And, okay. So even though at line 41 we're saying, hey, give us the memory for a rectangle, and we call area here for S1. Well, which version of area are we actually getting called here? It's just shape : area. Okay. No virtual, no runtime decision. It just says, oh yeah, this thing that you made, S1, we're just going to look to the left of it, like always, at what the type is, and it's a shape. Follow on here, and then yeah.
So if you I assume if you put a rectangle there, it would call it one rectangle.
Yeah, let's try it. Let's see here. So at line 41, I say, hey, this is a rectangle. Okay, here. Okay. Recompile. Oops, what happened here? What have I done? Did I spell something wrong? Rectangle. Rectangle. It says in function. Oh, private. Let's see. Okay, what did I do here? Oh, public here. Yeah. Okay. Oh, let's make sure this one's public as well. Okay. Cool. Compiles fine. Runs. Rectangle. Yep. Yes, fine. Let's try the other way. I think this was another question here. If I say, hey, this is a rectangle pointer, and we're going to do a new shape. Invalid conversion. Okay, so we can't go from down in our hierarchy and sort of go and say, hey, we're going to create this rectangle and then make it something simpler. So that instantiation isn't going to work here. Okay. Let's see, Jacob, you had a question.
So all virtual is doing, all the virtual keyword does, we compile, go to run, and goes, oh, okay, I see the word virtual. Let me just look inside of rectangle and see if there's a function labeled override.
Mm-hmm.
If we wrote virtual and then we wrote the other function, but we didn't write override, it would not do anything, correct? It would just use the shape one.
Correct. Yep.
Okay.
Yep. Yeah. And we can go.
So virtual just looks for the thing called override.
Yes.
That matches a function name. Or something.
Essentially, the override actually isn't necessary. It's as long as you put in just virtual once in your hierarchy, then it makes these objects that we would say is polymorphic, and saying, hey, it could take on many forms. We've got to sort of traverse and find the right function. I'm going to show you the mechanism in a second.
Cool. So is override more just like a visual thing more than anything people looking at it?
It is, yeah. What override will do, and let me go ahead and show you. So let me get us in a, I think this is our default state here. Yep, we've got override. I can actually omit at line 31 here, override. So let me get rid of it. And this example will work just fine here, okay, as before. What override is useful to do and why I would encourage to do it is, let's go ahead and say I do override here. Let's say I just misspell or something, capital A for area. And what override signaling is, it's saying, hey, look up in the hierarchy for something area that I will override. It will give you a compiler message that says, hey, you're trying to override. We sort of know you're looking up and down the hierarchy, but we didn't find it. Are you sure this is something that exists? And that's where it's useful. Yeah. So, yep. All right. All right, so let me compile this. All right. Okay, so does this make sense for folks? With virtual, whatever is on our, when we instantiate the concrete type on the right side, that's what we're actually going to look for. We're treating S1, it's a rectangle. That's what we're saying. Hey, give us memory, allocate this object here as a rectangle. Make sense for folks? All right, and then there was one question of, why wouldn't I just make this a rectangle here? And we should probably add something here. And let's see, perform. I'm just going to write a function here called perform operation. And we want to perform this operation on any type of shape here. So it's just a sort of freestanding function. So for a parameter, I'm actually just going to take in a shape here, call it shape, and I'll do shape area like this. Okay. So sometimes we like to use the base class or the and the thing on the top of our hierarchy, so we can write in sort of the most generic form what we're going to do. So for instance, this function here takes in a shape as a pointer, so that means it takes in any type of shape, rectangle, right triangle, right, all the different ones that we've looked at today, or just a regular shape here. So let's actually use it. Perform operation. I could pass an S1 here, and perform operation S2. Okay, it should compile, and it should run here, and it again calls the right thing. Let's try rectangle here. Rectangle. Let's see if it does the right thing here. Will it even compile? No, right? It's gonna again tell us, well, as soon as I try to pass in this, these things that are shapes, we can't do that here. If anything's derived from rectangle, we could, get a square or something else. I don't know, small rectangle or something. But that's why we would just say, when we write a function, just make it the most generic thing possible, and then at runtime, as long as we've allocated it properly and set up virtual, then we can, use this function in any way possible. All right? Does that make sense for folks? That's a good example of why we would write code this way. right? It's not just about, I think some folks, depending on what online tutorials you read, they say inheritance is a great way to save you from writing code, right? And that's true. That is a use of it. But the real use is so you can kind of write stuff generically like this and say, hey, this is something related. This is some operation we might want to perform on a bunch of shapes. And let's do it correctly here, right? Like this. So now I can write this one function. It's just going to operate properly on every shape, and then at runtime it'll figure out which is the proper way to compute the area for this shape, and so on. Okay, make sense for folks? Yes, a question.
What's the point of creating an instance of a shape? Like maybe this is just example specific, but like why would we want to create an instance of like the base type?
We might. I mean, in this case, I am very much using shape like what you'd call an interface in Java. I mean, it might have some functionality by default, right, that you don't know. This type of thing, and the advantage of being able to make this decision at runtime, right? I can delete shape S1, right? That's going to get rid of the rectangle, and then later I can come back and say, you know what? I actually want to treat this as a new rectangle or something, right? You can come back and kind of fix it. So maybe you don't know immediately. Again, since I do sort of game stuff, right? This would be sort of your like, hey, instantiate a generic artificial intelligence or something, and then you at least have something to work with, and then maybe something changes in the environment or whatever, and then you reinstantiate it to the actual type. Yep. And then otherwise where you'll see it, again, is like the most base class that you can use in a function, or maybe even in a and there's other mechanisms we'll learn about, but let's say I have a vector of shapes. Now all of a sudden I can hold rectangles, triangles, all these certain things in a collection, which is nice. And that's pretty powerful. Yeah. All right, other questions about this one? This is a nice example, or nice Q&A driven by you folks. All right, so virtual. Again, just means resolve at runtime. There's somewhere else you have to look in the hierarchy to find the actual function. Okay. All right. So what is virtual actually doing? How is it implemented? And again, this was the key takeaway we talked about, right? Virtual, use override. It's not required, but it's highly recommended. And there is final as well in C++, if you've seen that in Java, where you could say final override, and then nothing else can replace this behavior if there's stuff lower in the hierarchy. I don't have a great concrete example. When I do, I'll remind you of what it is. Okay, let's see how we are on time, and I want to just do a little something here just to show you what happens. There's a shortish, I think it's 10 minutes video or something, on probably one of the most frequent C++ interview questions. Let me turn the lights on just a little bit. So sorry, prepare yourselves. I wish this dimmer actually worked. It's either like all on or all off. So apologies to your eyes. All right. The way to do this is probably just to draw over here very quickly the mechanism for what virtual is actually doing. So just quickly here, create a struct. Here's our base class. Another struct here. Here's our derived class. And it's going to inherit from the base. And we should probably give it some function, right? So let's call this virtual. And and here we'll have print override, and you'll implement that somewhere else. Virtual. Okay. what does this actually look like in memory when I create this base and the drive? Same sort of things that we've laid out here. I'll just lay these out in a diagram here. Base, and again over here, drive. Okay. And maybe it's interesting too to create a little member variable here. Data. So base has data, and derived gets all the same attributes. All right. Now the question is, how do we know when I sort of write out this example here? I'll put it in a box. So for base star object equals new derived. So how do we know now that this object, the new derived object, so it's this type here, and I actually want to call this print function right here. Well, the answer to that is as soon as I create something that's virtual in my hierarchy, again, that means that I can treat derived as a base or type of class. What happens is we get this little additional pointer that's created in our data structures. It's usually something like this, underscore, underscore, VTBL. It stands for vtable or the virtual table. Okay. And what this does, it adds a little pointer here. You won't really be able to access it in your C++ code. I'm going to show you in GDB at the end of the class. But what this pointer does is it tells us which member function should we actually use. So it sort of routes us to the right member function. Okay, so there's a little pointer here, which label as a pointer. That goes out to some little table here. So for my base class, I've got whatever function for print that I should call. Okay. And let me actually write that here. All right, we've got the address of the correct print function for our base, which happens to be wherever this function is. Okay. Makes sense there. And then likewise for derived, we've also got the address of its print function. Okay? And what that's actually going to look like is derive print, just like we said. Okay? So that's what actually happens for our structures. Now you can imagine, again, if I don't have this print function here, then this little table here, right? Print doesn't exist. So, wherever this, I need a print function. So it's going to be routed to, somewhere up in my hierarchy. Okay. And that's the idea. That's what information the V table is for. All of the function pointers to the correct function in your hierarchy. Make sense? Question?
In the derived table, that app print, is that a pointer or is that a memory address?
I'm just saying this is the address of your print function, wherever it is.
Okay, so if it's pointing to the base one, it's just the address of the base one,
Yeah.
not a pointer to
Yep.
where the address is.
Yeah. So this literally is just a table storing addresses for your member functions. Usually how it's other questions about this? Common, folks will ask you, how is this implemented? So if you want to see this again, slower or a little bit more detail of me drawing the arrows, this is what's going on. Okay, if I don't have virtual, there is no vtable. Right? So let me, as I erase this, I'm going to get rid of virtual here in my print function. So there is no pointer here now. Right? C++ is really about performance. We don't waste anything. Right? So there's no vtable. Right? So we know exactly. This has its own print. Right? This has its own print. this stuff goes away here. Okay, there's no indirection following a pointer to some table that calls the right function. And that's the idea. So you can do a little search if you want. This will probably lead you to interesting implementation details. This isn't the only way to handle this sort of, again, polymorphism is the term we know, right? Where I say, hey, if I instantiate base as derived, I need to make sure that I call the right function. It's not the only way to do it, but this is probably the most common. Just store a table somewhere with a pointer to the right function. Okay, and that's how you can get away with, at runtime, this idea of saying, hey, a shape for now, I've instantiated as a rectangle, so do rectangle things. Or you change your mind and say, no, actually I'm going to point it to a new right triangle, and now it does right triangle things. Yeah, question?
So if base has a virtual member function, every derived class also has to have that.
Yeah, then it propagates. Yeah, we have to know which, because virtual means resolve at runtime, we have to know at runtime what to do. Although I guess if we made it final or something, maybe it might optimize or get rid of it. But yeah, in general, that's the rule of thumb. Add virtual once, and then you get a V table, a pointer. Yeah. Makes sense. Questions about V table stuff? Check it out. Do a little search. I'll show you at the end how you can look at this as well. The video is useful. I think I frame it as how to pass that interview question, because you will get asked, and it is interesting to know about. We don't care about performance yet in this class, but you can imagine, I'm following pointers and calling things. That has a cost too. That's why folks ask it. It makes your data structure just a little bit bigger, and then you also have to chase a pointer every time you want to do a function call. I forget, it might have been one of you folks is talking with last week, but and I think it's true. In Java, everything is a virtual function, right? By default, because everything inherits from object by default. Maybe there's a way to optimize that. Maybe somebody can Google it. But that's something you pay for, I guess. Actually, can somebody Google that really quick? Just let me. I think it is. I should have searched. Again, my Java's rusty. I haven't taught OOD. Let's see. All right. Actually, I'll look it up because we get a little break here. Let's break for 5 minutes till 4:08. Stretch your legs. I'm going to search the Java. In Java is everything a virtual method. They use method. Every non-static method. Okay, sure. Except for final and private. Okay, that makes sense.
Professor, can I ask you a quick question?
Sure.
So for assignment 7, I don't know if I need this, but I sort of use the SFML implementation of image as, if that's okay. Do I need to implement my own version of image?
No, that's
okay.
fine. Yeah.
Okay, so what I did was that I created an interface for a filter using virtual, and then I just had a bunch of I guess things that implemented the interface.
Yeah.
Just kind of create override.
Just the kernel or something. Yeah.
Override everything.
Seems like a good idea. Yeah.
Okay. I just wanted to double check if I just wanted to see.
Yeah, it seems fine. Yeah. me get us back in action. We got most folks back here. And moving along with some other object-oriented tools. Now we've just learned about virtual, which is a way to say, hey, at runtime we have to sort of figure out what type are we pointing to, and we have a via table that stores that information for us. So, another tool that's somewhat related is this idea of a interface. And by interface, I really mean an abstract class, or a class that doesn't really do anything, but just sort of serves as a true blueprint. And I've been using this term interface, which is our header file, so it's a little bit of a loaded term. But let me show you exactly what I mean in C++ here. So what I can do, and how I've been using this example, line 15 to 24 of shape here, is sort of as a, what I'd say, a blueprint, or in programming we call an interface, okay? And another way to describe this shape class would be to just call it an abstract class. Depending, again, what programming language you're using, you can just put the word abstract class, meaning it doesn't really do anything. You can't instantiate or create an actual shape here. But in C++, the closest thing that we have for this is to say, hey, we've got this class here. It's a shape. It has these member variables, width and height. And then we've got this virtual function here, a virtual int for the area, equals 0. Okay? And when I put equals 0 here, basically it means there's no implementation that I'm actually going to define here in shape. Okay, so I can't, again, instantiate something that's a shape and then call dot shape or arrow shape with it. Okay, it doesn't exist. But what this means is that any class that's derived from shape, so for example rectangle, it absolutely must implement this area function. Okay, and because it must implement area, then this sort of serves as an interface, or again a blueprint of behaviors that we want in anything that is a shape. Okay, does that make sense for folks? There might be many reasons to do this, and you might want to enforce this. I mean, maybe you just have functions like toString or something, or various functions like this that must be implemented that would be useful in your interface. Okay? So anyway, here's an example of this. And in C++, what we call this is a purely virtual function, which is basically our way of saying interface in C++. So purely virtual means it just exists. It's basically just a pointer to some implementation somewhere where it exists. It's purely virtual. Okay? All right, so folks understand that example? I'm going to run it and show you what happens here. Let's see here. Let me open up pure virtual. And what I'm going to do for this example here is just comment out this area function. Okay, so it's gone. And let's go ahead and compile it. And what's it going to say here? Well, we're going to get an error here. It's going to say cannot declare a variable r. So try to create r here at line 42. And it's going to say because the following virtual functions are pure within rectangle. Okay, so it's going to tell you, hey, you've got this class rectangle inheriting from shape, and then within shape, you've got this shape : area function here, right? It's purely virtual. Okay, so that means we must implement it. And again, this is a good way probably for you to implement a larger code base to enforce these types of things. Functions that must be implemented so that something's going to work properly. Okay, make sense for folks? Okay, so I'll go back here. I'll say, aha, I implemented area. Now can I, run this program? And yes, I can compile it and run it. And it doesn't really do anything. But now you can call the area function. It's been implemented. Okay, make sense for folks? All right, awesome. All right, so that's just on interfaces, covering our base there. So you could imagine now on, say, a homework, I could give you something and say, hey, here's your actual interface now, and now you must implement, these member functions, okay? Or more pragmatically, not just on a homework, but if you're building some sort of system, right, you can use this as a specification. Okay? And then, again, this is another area where inheritance is actually useful. You can enforce some sort of constraint on your code, okay, that it has this behavior. Okay, so that's just, again, on the motivation, why create these sort of abstract classes? Again, it's just sort of a clean way to ensure that some functionality is implemented. Because again, if I have this sort of generic shape thing that I've been talking about, it doesn't really make sense for me to even provide a default implementation of area here, right? Is it width times height? Is it width times height, or base times height times 1/2? What exactly does this mean? This is me saying, hey, you actually need to, for a rectangle and a triangle, those are two things that must have an area, but they're going to be different. So you have to implement it. We're not going to give you any default behavior. All right. Make sense for folks? All right, so this is good. All right, so just a little aside here. This is something that's allowed in C++, not so much in Java, so I don't know if you cover it or even look at it, but we're allowed to also use something called multiple inheritance. And basically what this means is, here's a little diagram. I can have in my hierarchy, so you can imagine class A being shape, and then maybe I have triangle here and rectangle. Then I could actually inherit some other property, or inherit from two classes, these properties. Not just two, but class B, class C, and class A. Okay? And probably a better use case for this, again, I'll try to give you a gaming example. Class A is a monster, okay, something that's bad. And then I want to say, okay, I've got these types of monsters, lizards. And I've got these types of monsters, flying monsters. Okay, and then the final drag type is a dragon or something, right? A flying lizard monster. Right, you sort of get the idea. So I'm gathering attributes from class A, B, and C, which are sort of different things, right? We've got things that fly over on this side of the hierarchy, things that are lizards over on this type, but they all are monsters, so that's fine. Then I've got this thing that wants, maybe the ability to fly and be a lizard, okay, a dragon, I don't know. So, here's what our class D ultimately sort of looks like, right? You get stuff from class A, you get stuff from class B, right? So sort of traveling on this side of the hierarchy. You get A, B, and then whatever's in D. And then I also get, what's on this side of the hierarchy, right? Which means, well, class A, or class C, is the type of A, so I get A, C, and D here. Well, that's kind of interesting. I get actually a repeat here, right? Because I've got to traverse, right? If I'm going to inherit from this, which inherits from this, I get all of this side. And I got to inherit from this and this, so I get all of this side. Okay, does that make sense? Everybody sees that there's a copy in here, class A. So that's one interesting thing. What else do folks think about this? What else makes this kind of interesting? Yeah.
If class B and class C both have like an overwritten function, like let's just take the area function,
Yeah.
and then class D calls the area function, but doesn't have its own overwritten, I don't know if it would go to B or C.
Yeah, it depends on the compiler, which is a bad thing, right? So for a while, the answer used to be, I think for a while, is whatever the compiler picks, right? It just says, oh, I've got this area function here, I found it. Okay, I'll use this one. But maybe you did truly mean this one, right? In our monster example, if I have a function called move here for lizards, right? They kind of crawl around. Flying monsters flap their wings. Which behavior are you trying to capture? The answer is, for a while, the compiler chose, depending on how you're building things together. You might get a compiler message. I think most of our compilers will say, hey, you've got area defined twice here. What do you mean? You can specify. You could say class B : area versus class C : area. So that is one problem, though. Yeah, it becomes ambiguous, which we don't like. Does anybody else notice other problems? So ambiguity is the big one they got here.
Double free.
Double free, yeah, because yeah, what if we've got we've got multiple copies of stuff? Let's see. Yeah, class A, right? We get duplicates. We've got duplicate stuff, maybe 2 pointers pointing to something. So this just kind of becomes such a disaster that if anything here is related, we generally don't allow this in languages, or we make it harder in languages to do today. Okay, so in Java, if you really work hard, you can create this situation. But by default, what you're going to learn is Java doesn't allow multiple inheritance. Right? Just one single hierarchy. Well, there is a slight way you can clean this up, and this problem has a name, just to give a name to it. So, right. So this is the again the idea of the ambiguity, right? And then if we have copies of stuff, right? If class A, since I've got a duplicate here, if that class points to 2, pieces of memory that are the same, we get double freeze, and that could be very nasty to figure out what's going on. But the name of this is called the dreaded deadly diamond inheritance, because we form this sort of diamond pattern here. Okay, that's generally bad. We try to shy away from it. You will see some examples of it. It can be used properly. The first thing that we probably want to do is get rid of these duplicate copies of A here. Or maybe we want them. I don't know. It depends. So if you want to do a little bit of a deeper dive on this, and this merits its own, if I can think of a good use case, we'll talk about it more in lecture, but in C++, we could use something called virtual inheritance, which lets us decide, do we want our hierarchy to look like this, where I've got some entity, that's a type of warrior, that's our, main character or something, or some other entity here that's a goblin, right? Do we want this sort of hierarchy here? We do have duplicates of X and Y positions. So we need to think a little bit about that. Or do I want the diamond pattern here? Okay. So if you want, that's a little bit of an aside here. It's a little bit out of scope for today. You can use something called virtual inheritance in C++ to fix this. All right. So that at least gets rid of the diamond. It gets rid of, and we still end up with 2 copies here. So the reality is when we want to use multiple inheritance, and hopefully we'll have a few minutes here in a moment to look and see if you can see where multiple inheritance is used in SFML. Because it is used, there are reasons to use it. We just have to be careful. Okay. All right, so really quick, any questions about this multiple inheritance? So really quick, I just want to show you in GDB. So we got to do a little bit of GDB. I'm going to dive into the virtual example that we were doing before. I can get rid of this. And I just want to show you how to look at the virtual table. So this will be useful for you to debug. So again, let me compile this. Let's run it in GDB. Silent. Program. Okay. All right. So let's start our program. Oops. Start. Okay. So again, this was an example, right, where we had shape, and I instantiate it as a rectangle, and I do this twice here. Once as a rectangle, sorry, once as a shape here. Okay, so I've executed this much code here. And then the question that I want to ask is, and pretend we're somewhere else, 100 lines down in our code or whatever. And I want to know, when I call area on S2 and S1, which actual version of area am I going to get? Okay. So let me execute one more line of code. There we are. I can type out info v table, which is abbreviated as VTBL on S1. And sorry, this is a little bit low for folks here. But what it's going to say is for shape, S1 here, and you'll see the actual address of the object. I'm calling in my v table here rectangle, : area. Okay, and does that line up with what we see for S1 here? We've instantiated new rectangle. Yes, we are good to go. All right, so the same experiment for S2. And this time we say info, give me the V table for S2 at line 49 or 50, whatever it is. What is it? Well, S2 is a new shape. So when I call area, I'm getting shape : area. Okay, so for my functions that were marked virtual, I'm able to call into the right one, and I can actually see it in GDB, which is super powerful. Not a lot of folks do that, but again, if you're in a big mess of code and you're saying, hey, it's not giving the right behavior, this is one of your tools that you can use. Okay, make sense? And then you can actually, remember what the V table is and tell your interviewer about it or something, and they'll say, wow, you know how to debug and the V table, you're hired, here's a bunch of money. And that's it. That's the end. All right, I got one little tiny exercise for you to do in a few minutes. Just with a neighbor, just take 2 or 3 minutes. We've got about 5 minutes, but take 2 or 3 minutes and open up the SFML documentation, find it, and with a neighbor, try clicking on some of these classes, maybe one that you've used. So someone just showed me image just a second ago, so let's look at image and see if you can find anything interesting about these. Now, this one actually doesn't look that interesting. There's nothing here, so I'm going to click on a different one. Let's try maybe font. Here, how about circle shape? I'll give you one to look at. But you will see these inheritance diagrams now. So now we can actually use them and take a look. Click on them, see what shows up, and just mention to your neighbor, like, hey, does this make sense? Or, yeah, would a circle shape be a type of shape? Why did they set this up? Are there other shapes that inherit from other things? Oh, look, multiple inheritance. Is that a good idea? And then maybe click and see, are drawable things related in any way to transformable things that could somehow get ambiguous? Just want you to take a quick look, introduce yourself with a neighbor, and then once you've done that, you've got the in-class activity. This will be part of the in-class activity just to mention what you find, and that's it. And I'll hang around here for a few minutes as well. All right, lights coming on as well. Brace yourselves. And I'll stop the recording here.
Earlier, I did circle shape, since you just put that up.